Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and we're going to cover some properties of determinants. So what I want to do is look at matrix A and matrix B, and I want to find the determinant of both these things. I'm also going to find matrix AB, which is going to be the product of these two matrices, and I'm going to find the determinant of that. And I want to see, is there some kind of relationship between products of matrices and products of their determinants? So let's go ahead and find their product real fast. So what we know is when I multiply the first row by the first column, I'm going to have 8 minus 10, which is minus 18. And then for this first row, second column, I'm going to have minus 12, minus 2, which is minus 14. Second row, first column, so minus 6 plus 5 is minus 1. And minus 9 plus 1 is going to be equal to minus 8. Now what I want to do is I want to find the determinant of both of these matrices. So when we set this up, let's go ahead and find the determinant of A and the determinant of B. So the determinant of A is going to be equal to, well, this is going to be 4 minus, this minus this. So 4 minus a negative 6. So this is going to be equal to 10. And then very similar with B, the determinant of B is going to be equal to minus 2 minus this minus 15. So minus 2 plus 15 is going to be equal to 13. Now what I want to do is I want to find the determinant of A, and in order to do that we have to, of course, multiply across. We have 18 times 8, and then both negative, so 18 times 8 is going to be equal to 144, so let's say matrix AB. Determinant, this is going to be equal to 144 minus a, positive 14. So this is going to be equal to 130. So now what we can see is when I look at these matrices, another way of saying that is this is the determinant of matrix A, we know is equal to 10. The determinant of matrix B is equal to 13. And what it's kind of looking like is the determinant of matrix A times B seems to be the product of these two determinants. It looks like this is going to be the determinant of A multiplied by the determinant of B, because the determinant of A is equal to 10 times 13, and we can see it indeed is equal to 160. So this will be our quick theorem. So what we have is theorem: if matrix A and B are square matrices of order n. Now the reason why we say they're square matrices is because to have a determinant they'll need to be square matrices. Then we can say this, that the determinant of matrix A times B is equal to the determinant of A multiplied by the determinant of B. And we're going to use this property actually to prove a lot of things. Now another property I want to cover is what happens when we have a multiplication of a scalar times a matrix. And what I've done is I've written this this matrix as something that is all divisible by 5. So we can see that this would be equal to 5 times the matrix 2, 3, minus 5, and then 1. So now what I want to do is I want to take the determinant of this matrix and then see how it relates to the determinant of this matrix. So what we'll say is this is going to be equal to some 5 times B, okay? So this is going to be B, and this is going to be equal to A. All right, so let's take the determinant of A. So the determinant of A is going to be equal to, multiplying across, we're going to have 50. And then minus, when I multiply across that way, I'm going to have a minus 15 times negative 25 is going to be minus 375. So what we're going to get is we're going to get 425. Now I want to take the determinant of B. B being this matrix after we factor out that 5. So that determinant is going to be 2 minus a minus 15, which in this case is going to be equal to 17. So, our kind of hope at first was that 425 would be simply 5 times 17, but it's not. It's actually equal to 5 times 5 times 17 because we know when we do matrix multiplication, this 5 will distribute to every element in that matrix. But when we're talking about determinants, they tend to be row dependent. So this 5 can go into the top row and this 5 can go into the bottom row to be able to produce this when we're talking about determinants. Because remember, it's this times this. So you can see the 5 will be here and also it'll be here. So really what we'd say is the determinant of this, so the determinant of our 5b is going to be equal to 5 squared times the determinant of b. 5 squared being 25, the determinant of b being equal to 17, which in this case is going to be equal to that 425. So that's really our next property when it comes to matrix multiplication. What we can say is if we have any real number c, then any c times matrix, any matrix is going to be equal to c to its degree, c to the nth power, because this was an n by n matrix, times the determinant of that matrix. So, next theorem. If A is a square matrix of order n, and C, say, is any real number, then we'd say the determinant of, say, C times matrix A is going to be equal to C to the n times the determinant of A. That's messy. Boop. And we can see that right here. Okay, so the last two properties I really want to go after is how do you show the last two properties I want to cover is verifying that a matrix has an inverse if its determinant is not equal to 0, and I'm going to use this theorem here to prove that. And I'm also going to use this theorem to prove how to find the determinant of an inverse as well. So let's go ahead and talk about this. The determinant of an invertible matrix. So a square matrix A is invertible or non-singular if and only if the determinant of A is not equal to 0. So let's go ahead and prove this. And we're going to start out with its implication. Like where does it ask us to begin? So it says a square matrix is invertible. So first, what we know, A is invertible. And what that means is that, it has an inverse. So we know that A inverse exists. That's what it means to be invertible. All right. So what we're trying to show is the determinant of A is not equal to 0. So only thing I know is that I have A and I have A inverse. And, these two things share a particular property. So from this idea, we know that A times A inverse is equal to the identity. So now what we get to do is we get to use this property here. So I know the determinant of the product is going to be the product of the determinant, so I'm going to take the determinant of both sides and then use this property. So we can say that the determinant of A times A inverse is equal to the determinant of the identity. Now we say IN if we say this is a matrix of order n, but we know it's a square matrix, so I can write I or I in there. And let's kind of talk about the determinant of, say, I2. So I want to find the determinant of, this matrix, which is going to be, 1, 0, 0, 1. And we know that the determinant of this is going to be this minus this, or that's also a triangular matrix. So it's just a multiplication of its diagonals, which is going to be equal to 1. And you'll see that it'll work for I3 and I4 and I5. So any IN essentially will give us the same thing, that the determinant of I is nothing more than 1. Now, using this property, the determinant of this product is equal to the product of the determinant. So I can say this is as the determinant of A multiplied by the determinant of A inverse is equal to 1. Which really, that statement proves that the determinant can't be equal to 0, because if I have the multiplication of two things equal to 1, then neither of those things are equal to 0. Because if this said 0, then I can say one or both of those things are 0. But since this is equal to 1, I can say that the determinant of A is not equal to 0, and the determinant of A inverse is not equal to 0. Really verifying that given this. Now the next one I want to do is I want to create a theorem that says if I know the determinant of A, I also can find the determinant of A inverse. And I am going to use essentially this. So here's kind of the theorem that I want to go after, and then see if you can spot it. So we'd say if A is an invertible matrix, non-singular, then we can say that the determinant of A inverse is equal to 1 over the determinant of A. And my claim for, this proof is sitting right above us. Almost. So what we know is we start out, if I want to do a proof here, let's kind of go fast through this. So if I want to do a proof of this, what I know is that, A is invertible. Which basically means A inverse exists. Now, if I know an A and A inverse, I know that their main property says that A times A inverse is equal to I. Or, if it suits you better, you can say A inverse times A is equal to I. So it doesn't really matter the order in which you multiply these things. So I'm going after determinants, so I don't really need this right-hand side. I'm just going to say that, the determinant of this side would be equal to the determinant of this side. And the determinant of the product is the product of the determinant, so this is the determinant of A inverse. I know this looks extremely familiar because it's written right above us. Is equal to 1. Now remember that what I'm trying to show is I'm trying to solve for that thing right there. So since this is multiplication right here, I can divide both sides by the determinant of A, so I can say that the determinant of A inverse is nothing more than 1 over the determinant of A. Proving that. Let's see, I'm also proving this. Little squares just mean that the proof is done. Alright, so wrapping up, we have one more theorem to cover, and then we'll do like a little capstone of if I give you like the determinant of A, the determinant of B, can we find some certain properties? Or the determinant of some certain things. So the last theorem I want to cover is how do you find the determinant of A transpose? And I'm going to just show you through an example of a 3x3 matrix and talk about how we can find the determinant of A transpose as opposed to the determinant of A. So say A is equal to this matrix. We have 7 minus 2, 1, 3, 4, 8, negative 2, 6, 5. Okay. And my goal really isn't to completely find its determinant, but what I know is I know that A transpose is going to be all rows become columns. So this will be 7 minus 2, 1. This will be 3, 4, 8. And this will be minus 2, 6, and then 5. All right. So when I want to find the determinant of these things, I'm really just going to use a cofactor expansion. And since it doesn't really matter, nothing's advantageous, I don't see a bunch of zeros, I'm just going to do a row 1 expansion here. So, the determinant of A is going to be equal to 7 times, this matrix down here I have 4, 8, 6, 5, minus that minus 2 times a, these outer ones, 3, 8, negative 2, 5, and then finally plus this 1 times this determinant of over here we have 3, 4, negative 2, and 6. Now, what I want to also do is find, say, the determinant of A transpose, and I would like it to kind of look the same just to make sure that we have something similar. So if I was going to find A transpose, what kind of expansion would I use for this to show that I get the identical thing? So since all rows become columns, if I'm using row 1, what I'm going to do is I'm going to use column 1 right here. So that is going to be 7 times, the matrix 4, 6, 8, 5, minus that minus 2 times the matrix 3, negative 2, 8, 5, and then finally plus the 1 times the matrix 3, 4, 3, negative 2, 4, 6. Now I know they don't look exactly the same, but you can see that, these coefficients here are the same. I know the matrix look a little bit different, but let's just double check. Like when I do the matrix, it's going to be 4 times 5 minus 8 times 6. That's what I have. 4 times 5 minus, 6 times 8, which is 8 times 6. So that determinant's going to be the same. Same thing here. This is still 3 times 5. This is still the product of 8 and negative 2. And same thing here. This would be 3 times 6, and then this also be here, just like this. Now, if they were bigger, the expansion is just the same. You just have to, have a bunch of nested 3x3s, and eventually you bring them down to 2x2s that have this, equivalency as far as their products. So here's kind of the capstone. I'm going to give us like a couple matrices and their determinants, and I'm going to ask you to find the determinants of things that are related to them. Okay. So here's our capstone example. What I want to do is I want to find if I give you if I give you A and B are square invertible matrices of order 3, so they're 3x3 matrices, and I know the determinant of A is equal to 7, the determinant of B is equal to negative 2. Can I find, say, the determinant of A times B? Or we can say this, right? Looks like absolute values. B. Can I find the determinant of, say, A inverse? And C, can I find the determinant of 4, say, B? And then finally, D, can I find the determinant of, say, A transpose? Okay, so if I want to find the determinant of A times B, well, I know that this is equal to the determinant of A times the determinant of B, and the determinant of A is 7, the determinant of B is negative 2, so this is equal to minus 14. If I want to find the determinant of A inverse, what I know is this is 1 over the determinant of A, so this is going to be 1 over 7. If I want to find the determinant of 4B, well, I know that this is going to be equal to 4 to the nth power times the determinant of B, where n represents the order of the matrices, because really all I'm going to do is I'm going to factor in 4 out of all 3 lines, because this is a 3x3, so this is 4 cubed times the determinant of B, so 64 times a negative 2, which is going to be equal to minus 128. And then last, the determinant of A inverse is nothing more than A transpose is nothing more than the determinant of A. So this is going to be equal to just simply 7. So if you like the content, please subscribe.